In this module, we'll talk about the Q10 effect. The Q10 effect is essentially a tool that allows us to describe how reaction rates change as a function of temperature. Generally speaking, as temperatures increase, the rates of reactions increase also. And as temperatures decrease, the rates of reactions decrease. This is true both outside of biology as well as within biology. In biology, of course, many reactions are catalyzed by enzymes. So these principles apply to enzymatically catalyzed reactions as well as non-enzymatically catalyzed reactions. As a rule of thumb for biological reactions, for every 10 degrees Celsius increase in temperature, there is a corresponding increase in the reaction rate of approximately 2 to 3-fold. Similarly, for every 10 degrees Celsius fall in temperature, there is a corresponding decrease in the rate of the reaction of approximately 2 to 3-fold. If we look at this graph and we want to ask, what is the change in the rate of the reaction in going from, say, 20 degrees Celsius to 30 degrees Celsius, all we have to do is start from the x-axis at 20 degrees Celsius, go up to the curve, go over to the y-axis and ask, what is the rate of the reaction? It looks like about 4. If we do the same for 30 degrees Celsius and go over to the y-axis, it looks like the rate of the reaction is about 8. So in going from 20 degrees Celsius to 30 degrees Celsius, the change in the rate of the reaction is approximately 2-fold. This means that the Q10 effect for this reaction that's shown in this graph is approximately 2. So why is it that the reaction rates change as a function of temperature? The reason for this is that chemical reactions require that reactive groups for molecules involved in the reaction adopt a particular orientation in order for a productive reaction to occur. As temperatures rise, the kinetic energy within the system increases. That means that molecules move around a lot more, and therefore they more frequently adopt orientations that are productive for a particular reaction to occur. And therefore, as temperatures rise, reaction rates increase. Reaction rates do not increase indefinitely in biological systems as temperature rises. At some point, reaction rates start to plateau, and then they even start to fall off. And this is due to the fact that the enzymes that are catalyzing the reactions are starting to denature or starting to unravel at that temperature. As a result, all biological reactions have an optimal rate that is essentially a balance between the Q10 effect and denaturation of proteins. This optimal rate occurs at an optimal temperature that is specific for a particular enzyme that catalyzes the reaction. In many biological reactions that occur within humans, the optimal temperature is around 37 degrees Celsius, and that is because these enzymes were evolved to function most effectively at around 37 degrees Celsius, which is our normal body temperature. The Q10 effect can be described by an equation, and the equation is shown here. On the left, we have Q10, and on the right, we have a ratio of two different reaction rates, R2 and R1. That's raised to the power of 10 degrees Celsius divided by a difference of two reaction temperatures, T2 and T1. So reaction temperatures T1 and T2 must be in units of degrees Celsius, and those must correspond to reaction rates 1 and 2 respectively. And so if we know two reaction temperatures, and we know two reaction rates that correspond to those temperatures, we can plug those values in to this equation to determine what the Q10 value is for that particular reaction. So let's look at an example. So let's say we have a reaction and we want to determine the Q10 for that reaction. We can measure the reaction rates at two different temperatures, say T1 equals 20, T2 equals 30, and we get reaction rates of 3 and 8 for those two different temperatures. We can then plug those values in to the Q10 equation, and so we have R2 is equal to 8 divided by 3, which is R1, raised to the 10 degrees Celsius, divided by 30 degrees Celsius, T2, minus 20 degrees Celsius, T1. 10 divided by 10 is equal to 1, 8 over 3 is equal to 2.67, so we have 2.67 raised to the first power, which is equal to 2.67. So in other words, in going from 20 degrees Celsius to 30 degrees Celsius, our reaction rate increases by 2.67-fold, from 3 to 8. So it turns out that the order that we use for T1 and T2 does not matter. We can actually reverse the two temperatures and use the higher temperature for T1 and the lower temperature for T2, as long as we also reverse R1 and R2 that correspond to those two temperatures. If we do this, we can now plug in our reaction rates. R2 in this case is 3 divided by R1, 8, raised to 10 degrees Celsius divided by 20 minus 30 gives us 0.375 raised to the minus 1, which is 1 over 0.375, or 2.67. So we get exactly the same Q10 value, whether we use the higher temperature for T1 and the lower temperature for T2, or the lower temperature for T1 and the higher temperature for T2. So let's say that we know that Q10 for a particular reaction is 2.5, and we know that at 30 degrees Celsius, that reaction goes at a rate of about 10. And let's say that we want to know what is the rate of the reaction at 10 degrees Celsius, or 20 degrees Celsius lower than the rate that we had measured at. To find this value, we can rearrange the Q10 equation. And if we do that, we get a modified equation that looks like this. So we have R2 equals R1 times Q10 raised to the T2 minus T1 divided by 10 degrees Celsius. So again, we can plug these values in, and if we do that, we can solve for R2. So in this case, we get R2 equals 10, which is our R1, times 2.5, which is Q10, raised to T2 is 10 degrees, minus T1, 30 degrees, divided by 10. This gives us 10 times 2.5 raised to the minus 2, or 10 times 0.16, which is equal to 1.6. So what we found is that as we go from 30 degrees Celsius to 10 degrees Celsius, our reaction rate drops from 10 to 1.6. Oftentimes, Q10 values are determined by plotting reaction rates as a function of temperature. So in the example shown here, we've plotted a metabolic rate as a function of temperature going from 7 degrees Celsius to 17 to 27 to 37, and what we found measured is the reaction rates or metabolic rates that occur at those temperatures. So we get 5, 10, 20, and 40 watts per meter squared for our metabolic rates. So from this data, we can now use this to calculate Q10. So to calculate Q10, all we have to do is pick two temperatures, take the values for metabolic rate that correspond to those two temperatures, and plug them into the Q10 equation. So in this case, we're going to pick 37 degrees Celsius as our T2, 17 degrees Celsius as our T1. We get a reaction rate 2, R2 of 40, and R1 of 10. We can then calculate from these values that Q10 is equal to 4 to the 0.5 power, which is the same as saying the square root of 4, which gives us a Q10 of 2. And so the important point here is that we could choose any two temperatures, plug them in here, as well as the corresponding rates, and we should get the same Q10 value regardless of which temperatures we choose.